Hello, welcome to this video on work, energy and power examples, and these are the first couple of questions. And the first one that I wanted to have a look at is this one. Calculate the power of a pump which can lift 200 kilos of water to a vertical height of 6 meters in 10 seconds. So the equation we're going to use here is power equals the work done per unit time. Okay, and if you have any doubt about where this equation comes from or what it means or what work done is, then go and have a look at the videos on theory, which are in the different playlist. So let's see, we need to know what the work done is in this by this pump during these 10 seconds. So let's see, what is work done? Work done in this case is going to be the amount of energy that is transferred to the water, and since we're moving vertically, the water will receive potential, a change in its gravitational potential, and the increase in gravitational potential will be at exactly the same amount as the work done. So if we lift 200 kilograms 6 meters, then our delta potential energy, which is we're going to calculate, would be divided by the 10 seconds, which is the time it takes, would be mgh, which is 200 times 9.8 for the gravitational acceleration, mg, and h is 6 meters. All of that divided by 10, that would be the amount of potential energy gained by the water because of the work done by the pump. So all the work done by the pump is exactly the same as the potential energy gained by the water, and this is because it's a 100% efficient pump, or this is the useful energy, the useful power of the pump. So we're really calculating how much of the power is useful, but assuming it was 100%, then it's also the power of the pump itself. So let's calculate this. It is 200 times 9.8 times 6, 1176 joules, watts, 1176, and the units of power is joules per second, which is the same thing as a watt. And to three significant figures, this would be 1180 watts. So that's how much energy it does every second, or how much work, how much energy, potential energy it gives the water every second, or how much work the pump is doing. That would be the answer of our question. So let's have a look at question 2. I'm just going to write it out and pause it and write it out, and then continue when it's written out, so we don't waste time. Okay, and as with magic, there it is. It's, just before we go into the second question, I wanted to mention something about the first one. The reason why all the power of the pump is going into potential energy here is because the water is being raised up vertically, and there is no resistance or any losses of energy, right? If there was any loss of energy, or there was any resistance to fight against, then some of that power would go into other forms like heat and sound or whatever. But since here we're dealing with only a transfer from work by the pump into potential energy, then we take it to be only that. Okay, so that's why we can just do this calculation like that. The question kind of implies that we can do that. Okay, so hopefully that makes sense. Now in the second question, it says a boy whose mass is 40 kilograms can run a flight of 45 steps, each 60 centimeters high, in 5.2 seconds. What power does he generate? Okay, so again they give us a mass and they give us an amount of height, 45 steps of 60 centimeters, and an amount of time. So you can look at it in the same way again. You can say, well, the power that he's going to have to display is going to equal the amount of work that he does divided by the time. And again here, the amount of work that he does is going into potential energy, his own potential energy as he rises up the steps. So the change in potential energy divided by the seconds, which is 5.2, and this change in potential energy is his own mass, which is 40 kilos, times the gravitational potential, which is 9.8, acceleration due to gravity, or the gravitational field strength, and then h is 60 centimeters times 45 steps, so that's 45 steps times 60 centimeters, and 60 is not in meters, so we've got to multiply it by 10 to the minus 2 so that we can get it in meters. So all of that divided by 5.2 will give us the amount of power that he generates. I'm going to do this in the calculator. Okay, just saved, pause it to save a bit of time. It's 2035 point something 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 035, but we wanted to 3 significant figures really, so this is joules per second or in watts, and that to 3 significant figures, that would be, well, this is a significant figure, this is also a significant figure because it's after a non-zero number, and finally the 3 needs to be rounded up because that's a 5, so it would be 2040 watts to 3 significant figures, and that would be our question done. Okay, hopefully that makes sense. I'm now going to write question 3 down, and I'll also pause it again to save you a bit of time. In the third question it says that a stone of mass 500 grams is thrown vertically upwards with a velocity of 15 meters per second. Find its potential energy at its greatest height. Now they don't tell us anything about air resistance, so well, actually at the end of the question it does say, it says neglect air resistance, so we're going to ignore that, which is convenient, and they give us an initial velocity for when the ball is at the bottom, so using conservation of energy, we're going to treat this as a closed system, or we're going to say that energy is not, it's conserved, it's not lost or created or destroyed, and since there's no air resistance, there's no transfers to any other type of energy, so all of the initial energy that the ball has will go into gravitational potential energy when it's at the highest height, the greatest height. And this will mean that its initial, so we're going to use conservation of energy, so we can say using conservation of energy, we know that the kinetic energy plus the potential energy is going to be a constant. They both together are a constant, and at the very beginning it's all kinetic energy. There's no potential energy with respect to its own height because it's got a zero height with respect to its own position. So if we're measuring the base from where we throw the ball, if we throw the ball from here and we take this to be zero height, then mgh is equal to 0, so the only energy that this has at the beginning is kinetic energy. So we can then say that therefore kinetic energy at the bottom equals the potential energy at the top. Since the addition has to be a constant, then when we only have kinetic energy, that will be equal some value, and at the very top we only have potential energy, we have no kinetic energy, and that value will be the same since this is a constant. So we then say that the kinetic energy at the bottom equals the potential energy at greatest height, and therefore we can use the formula half mv squared, where the squared only affects the v, is equal to mgh, and half mv squared is half times the mass. So we're going to continue here, so we can say half times the mass, which is 500 grams or 0.5 kilos, times the velocity squared, and velocity is 15 squared. That will be equal to the potential energy at the greatest height, maximum potential energy, which, let's see what that is, 15 squared times 0.5. I start from the right to the left because that way I can do the squared already and make less mistakes, times 0.5 times 0.5 again, because 1/2 is also 0.5, so that's 56.25. 56.25, which to three significant figures is 56.3 joules. So that will be our potential energy at the maximum height. Okay, so I hope that's alright. And in the second part it says it's kinetic energy upon reaching the ground. Well, if there's no air resistance, the kinetic energy is going to be exactly the same again. So we can then say, using conservation of energy also, that the kinetic energy plus the potential energy equals a constant. The potential energy on the ground we take to be 0. So we're defining it to be 0, and therefore the kinetic energy when it comes back down again, therefore the kinetic energy on the ground is equal to the same thing again, which is 56.3 joules. Now they don't ask us to do this in the question, but I want to do it just so that we get a bit of practice with it. Let's try to find out the distance, the height at which it reaches. So let's try to find out the height, the maximum height reached. So we know that 50. Let's take the full answer so that we don't make mistakes, which was 56.25. So 56.25 is equal to the initial kinetic energy, the kinetic energy on the ground, which is equal to the potential energy on the top, the maximum height. So in other words, mgh is equal to 56.25, and so h is equal to 56.25 divided by mg. mg is 0.5 times 9.8. And we get 11.479, which is 11.5 meters. That's how high it goes. So that was very easy to calculate if you want to know the maximum height, right? If you wanted to do it in the other way, where you want to use the velocity equations, then you what do we have? We've got the initial velocity, which is 15. We've got the final velocity, we know it's 0 at the top, and we've got the acceleration, which is minus 9.8. So you've got three things, so therefore you can calculate any of the other things. So we can calculate the height, and we would use there v squared equals u squared plus 2as. You can do it if you want on your own, so that you can find out that if you rearrange this, s equals v squared minus u squared over 2a, you will get the same thing. But you can see that this is already a little bit more messy than the other method. This was very quick. I hope that makes sense, and we'll do some more questions in the next video. Until then, take care.